Welcome back, students, to Unit 4b, Covalent Compounds. Today we will be talking about the valence shell electron pair repulsion model, or VSEPR theory for short. In this unit, we have been talking about what holds atoms of nonmetals together, and it's those valence electrons that they share. Those shared valence electrons attract the nuclei of their atoms closer together to allow them to reach a lower energy state. If those electrons appear in the same plane as the nucleus, these are known as sigma bonds. That's the technical jargon for every connection we've drawn for an atom is a sigma bond. So when we drew methane, the carbon atom of methane has 4 sigma bonds. In carbon dioxide, the carbon atom of carbon dioxide had 2 sigma bonds. A sigma bond is the connections between two atoms. Pi bonds are anything after those connections. And for methane, there are no pi bonds, as there's nothing after those connections. However, for carbon dioxide, with its 2 double bonds, each of those double bonds is 1 sigma and 1 pi bond for 2 pi bonds in carbon dioxide. You can look at the sigma and pi bonds of a single atom or of an entire compound. If we look at ethanoic acid has 1, 2, 3, 4, 5, 6, 7 connections, or 7 sigma bonds, in a single double bond, which would give us 1 pi bond. Ethanoic acid as a molecule contains 7 sigma bonds and 1 pi bond. More electrons bonded between atoms increases the negative charge between those two nuclei, pulling the atoms closer and closer together. Known as its bond order, bond order is the relative strength of one atom to another. You can also think of it as the distance between two nuclei, the length of a bond. So a triple bond with lots of with 6 electrons between the two nuclei, pulls the atoms closer together. A triple bond is the shortest of bonds, so a bond order of 3 is the shortest, and therefore the strongest. Triple bonds are the strongest of covalent bonds. A double bond would be slightly weaker. A bond order of 2 is a little bit longer, while a bond order of 1, a single pair of electrons shared between two atoms, would be the longest, and therefore the weakest of covalent bonds. There are such a thing as fractional bond orders, and this occurs when you are able to draw a Lewis structure more than one way correctly. If we were to draw nitrate, you might end up with a structure like this, putting the double bond on the right side. However, you could just as easily have ended up putting the double bond on the left side. Both of these Lewis structures contain the correct number of electrons, and both of them are valid. Since they are both valid, they are what's known as a resonance structure. Resonance structures means that this double bond actually appears in both locations. It resonates between the two oxygens, flip-flopping from one to the other, causing the bond length, the bond order of this bond, to be slightly longer than a double bond, but slightly shorter than a single bond. So fractional bond orders are when you draw a Lewis structure and there's more than one correct answer. Now, when those atoms share electrons, they are doing so pushing together their valence shell, and those electrons take up a certain amount of space, so the atoms have to mush together a certain number of their orbitals or hybridize them to make space for all of those electrons. The amount of space they need to make deals with their regions of electron density, the places around an atom where electrons can be. So this includes lone pairs and bonded electrons, where each bonded location counts as a single region of electron density. So back to our examples of carbon with methane or carbon dioxide, or the example from last class, cyanide. Hybridization requires you to look at a single atom. So for the carbon in the center of carbon dioxide, its electrons can be in two locations, either in the bonded pair on the left or the bonded pairs on the right. There are two regions of electron density for carbon dioxide. Each of those regions will require us to hybridize two of our valence shell, our outermost orbitals. So remember, the outermost orbitals are the s orbital, the p orbital, which can hold 6 electrons, so 3 distinct shapes, and if we're dealing with very large atoms, we could hybridize our d orbitals, because some atoms are able to have an expanded octet. So having two regions of electron density means carbon dioxide is going to have to hybridize two of its orbitals. So carbon dioxide, we would say, is sp hybridized. In cyanide, carbon has two places electrons can be. It can be in the bonded pair or in this lone pair. So since it also has two regions of electron density, cyanide is also sp hybridized. With 4 regions of electron density, methane would need to hybridize 4 of its orbitals, so s and p, as well as the other 2 p's, giving us spp or sp cubed, sp3 hybridized. When atoms have expanded octets, we will start pulling in the d orbital. These hybridizations force atoms to take on particular shapes. In class, we have drawn our Lewis structures as flat crosses or lines simply because we are working on a flat surface. However, in reality, atoms take on very distinct and odd shapes based on how many electrons they have to house around them. And unfortunately, you must know what these shapes are based off of their valence shell repulsion, or VSEPR. In class, we will talk about this, and in class we used a simulator to show it. So let's pull up the simulator for valence shell electron pair repulsion model, or VSEPR. For carbon dioxide, our Lewis structure comes out something like this. And when we look at a molecule of carbon dioxide is a linear shape, which means that between these two oxygens, the bond angle is 180 degrees. Personally, I remember the bond angles follow the hybridization. Carbon dioxide is sp hybridized, and in my mind, anything that's sp hybridized has to be a linear shape with a bond angle of 180 degrees. This is information that my mind works off of. I use the hybridization to justify my shapes and bond angles. If an atom has 3 bonds, like boron trifluoride, drawing the Lewis structure for boron trifluoride would give you a structure like this. Boron has 3 regions of electron density, therefore it is sp2 hybridized. sp2 hybridized means that this takes on a trigonal planar shape. It is a flat triangle that lies flat in one plane. As a flat triangle, it has a bond angle of 120 degrees. Again, in my mind, I keep track that anything sp2 hybridized is trigonal planar with a bond angle that starts at 120 degrees. I say it starts at 120 degrees because when things are sp2 hybridized, you could replace one of these bonds with a lone pair. You would still be sp2 hybridized, but you are no longer going to be trigonal planar. An example of this would be sulfur dioxide. Sulfur dioxide is still sp2 hybridized, and the bond angle is supposed to be 120 degrees. However, lone pairs have an excessive amount of energy, meaning they take up way more space, and since they are negative, their electrons, they repel the bonded pairs, reducing the bond angle. Now, In this class, I am not expecting you to know the exact bond angle. I just want you to know that when you have a lone pair, the bond angle is reduced. So while things that are sp2 hybridized normally have a bond angle of 120 degrees, the lone pair is going to reduce that bond angle from 120 down to something less, like 119. You do need to know, though, that this is called a bent shape. So sp2 hybridized with one lone pair leads to a bent shape. Things with 4 regions of electron density, like methane, those which we draw flat on the board, in reality will repel one another to be the maximum distance from each other. Those bonded electrons of hydrogen are going to spread each other out, producing a 4-sided dice shape known as a tetrahedral. So while we might draw it flat when we draw our Lewis structures, in reality, those 3 hydrogens are kind of coming off the bottom, with 2 of them, the one up and the one maybe to the right, in the same plane, like this image might show. You have one that comes towards you. So we sometimes show that as a triangle that's getting bigger, and one that goes away from you, and things that go away come to get a little blurry, so we show that with hashed lines. Here we show a 3-dimensional image on paper of methane. Methane, with its 4 regions of electron density, has to have 4 orbitals which we merge together. So that would be sp3 hybridized. Anything that's sp3 hybridized, my mind remembers, is 105 degrees, and it starts as a tetrahedral. As we start replacing some of these with lone pairs, those bond angles will drop. So to go from methane, an example of something with 4 regions of electron density and 1 lone pair, the classic example is ammonia. Ammonia has 4 regions of electron density with a single lone pair. That lone pair takes up residence above the bonded pairs, causing the bond angle to drop. And again, while no one expects you to know the exact bond angle, I do expect you to know that 1 lone pair with 4 regions of electron density means that the bond angle is going to be a little bit less than 109.5. This shape is no longer called a tetrahedral. It is now a 3-sided pyramid we call trigonal pyramid. So a trigonal pyramid shape, the classic example is ammonia. If you have 4 regions of electron density with 2 lone pairs, a classic example is water. In this course and in biology, you've often seen us draw water as a pair of Mickey Mouse ears. Today you learn why water takes on a classic bent shape, with the 2 lone pairs taking up space around that oxygen. The bond angle is substantially less than 109.5, down to 104.5. And this again is called a bent shape. Atoms with 5 regions of electron density cause our shapes to become a little more distinct. Phosphorus tetrachloride, if you were to draw the Lewis structure, you'd end up with something similar to this, ignoring the lone pairs on all the chlorines. Phosphorus tetrachloride actually is 2 shapes. Along the middle, we find a tutu of sorts of chlorines. So along the middle, our bond angle comes out to 120 degrees. Something that is sp3 dehybridized, so 5 regions of electron density, have actually 2 bond angles, 120 degrees along the middle, and from top to bottom, you end up at 90 degrees. So we have 2 pyramid-like structures. 2 3-sided pyramids means that this is known as a trigonal bipyramid. Again, the bond angles start at 120 degrees and 90 degrees. Adding lone pairs, however, is going to cause this shape to change drastically. So sulfur tetrafluoride, we've replaced one of the bonded pairs with a lone pair. We still have 5 regions of electron density. This is still dsp3 hybridized, but now it has 1 lone pair. Since we have 1 lone pair, that lone pair is going to occupy one of the parts of the tutu along the center, creating a shape that's called a seesaw shape. because it looks like a seesaw. That lone pair causes the bonded pairs to reduce their bond angle. The exact numbers are not important. It's important that you know that it started at 120 and 90 degrees, and now it is less than 120 and 90 degrees. With two lone pairs, another bonded pair is replaced in the 2-2, and we end up with a molecule that has a T shape to it. So chlorine trifluoride is T-shaped. The two lone pairs cause the bond angle to drop some more, but this is a nice pretty little T. If you have 3 lone pairs and 5 regions of electron density, we actually go back to a linear shape, as the lone pairs take the place of the entire 2-2, replacing all the bonded pairs in the middle, and only your top and bottom stay intact. So xenon difluoride is linear. Lastly, if you have 6 regions of electron density, you require 6 orbitals. So we are D2sp3 hybridized. This forms an 8-sided dice known as an octahedral. Octahedrals, or 8-sided dice, all have a bond angle of 90 degrees. Adding lone pairs will change this bond angle slightly. So replacing one of the bonded pairs with a lone pair gives us a 4-sided pyramid. So since it has 4 sides, we call it a square pyramid. So D2sp3 hybridized with 1 lone pair is square pyramid, and the bond angle is a little less than 90 degrees. 2 lone pairs will bring us to the end of this little song and dance number. 2 lone pairs replace the top and bottom bonds, creating a flat square. So to say flat in chemistry, we say planar. This is a square planar molecule, and the bond angle actually returns to 90 degrees. I realize this is a lot of information to handle, therefore you will find on the website a link to a Quizlet that I formed a few years ago, which has the shape as well as a picture and the hybridization. You do need to be able to identify the shape from the hybridization based off of your Lewis structure. So you would start by drawing a Lewis structure and then lay out what its shape or hybridization is. The reason you need to be able to do this is because next class we will take a quiz. On that quiz I will give you 2 formulas, like say methane and carbon dioxide, and I will ask you to draw their Lewis structure. So you would have to count up your valence electrons, divide by 2 to figure out how many pairs you have, put your central atom in the center and connect it to your terminal atoms, giving every atom their lowest energy configuration by using up pairs, and then make sure everyone is at their lowest energy state, meaning everyone's got 8 or the amount they need. Once you have drawn your Lewis structures, I will tell you what their bond angles are. I will say, for example, that methane has a bond angle of 109.5 degrees, while carbon dioxide has a bond angle of 180 degrees. And I'll ask you why. You will have to point out that they are different shapes. Pointing out their different shapes is only enough to get you partial credit. You actually will need to tell me what their shapes are and why. You would have to reply that methane has 4 regions of electron density, therefore it is sp3 hybridized, which makes it a tetrahedral. While carbon dioxide has 2 regions of electron density, and therefore is sp hybridized or linear. From there, I will move on to something completely different. Say, example, I gave you ethanoic acid and expected you to tell me how many sigma and how many pi bonds. You would have to count your connections as sigma bonds and anything after that as pi. You also will have to tell me the hybridization of one of the carbons or one of the atoms in that molecule. Meaning I'll point to one and say, what is its hybridization? You would have to identify it as 1, 2, 3 regions of electron density, so this would be sp2 hybridized. Lastly, I'll point out an oddity, that boron only makes boron trifluoride, while germanium can make boron trifluoride or germanium tetrafluoride. Why is there only one type of boron fluoride? And you'd have to point out that boron can violate the octet rule as its nuclei is too weak. Or I might go the other direction. Why is there only one type of oxygen and there's lots of types of sulfur fluorides? You have to be able to identify elements that violate the octet rule either with too few or too many, and be able to explain the expanded octet or a weaker nuclear charge. And that's our quiz next class. In order to do well, I highly suggest you get comfortable with the valence shell electron pair repulsion model as well as hybridization.